Welcome back, folks. So in this video, I actually want to talk about what this dot product actually is. Alrighty. So before we actually talk about dot product, and you're going to see in a second here, it's a way of multiplying vectors. I want to just kind of take stock of what we already know. Okay. And so what I want to take a look at is just what happens, when we do these operations first with just regular numbers or scalars, and then talk about what it means to do these operations with vectors. Okay. Here's what I mean. So we know all about scalars at this point. We've been playing around with them, since we were little kids, really. So for example, if I take two scalars, sorry, my pen's being weird. If I take two scalars, so again, a scalar is just a fancy word for a number with no direction, or a quantity with no direction. A scalar, and I add it to another scalar. What comes out? Well, an example of this could be just, 7 plus 6, and the answer comes out to be 13. 13 is, again, just another number. And so when I add two scalars, well, we simply end up with another scalar. Same happens when we multiply, so we'll just real quick show this. If I take two scalars and multiply them, you'll end up, again, with another number, a scalar. I don't know why I'm putting parentheses around them, but I am. Okay, so that's all fine and dandy. We have now also talked about, what it means to add two vectors, or I've showed you some videos in this playlist. So if I take a vector, and I add it to another vector, well, we've seen this before, so let's pretend I add this green vector to, say, this blue one. All that simply means is to take this blue one, or the green one, again, we know that vector addition is commutative, and the end result is, this one. That is the resultant vector, R. And so that is really just another vector. So you take two scalars, add or multiply them, you'll end up with another scalar. You take two vectors and add them, you'll end up with another vector. We've also seen this scenario, which is a little unusual, if you think about it, but it's not too bad, where we take a scalar and multiply that by a vector. Remember, an example of this could be 2 times the vector, call this vector, vector v. What would that look like? Well, again, the resultant vector is just that same vector, just it's stretched twice as long. And so this ends up looking something like this, where the length is, again, twice the original length. But at the end of the day, it is just another vector. Slightly different than the original vector, but only in length. Okay. So scalar plus scalar equals a scalar. Scalar times scalar equals a vector. Vector plus vector equals a vector. Scalar times vector equals vector. The one that we have not talked about yet, and what we're going to address in this video, is vector times vector. What should that be? And I just want you to kind of think about that for a second. Now, I don't know about you, but my gut feeling, and I don't really have an explanation as to why this is my gut feeling, that's why it's a gut feeling, is that when I take two vectors and quote unquote multiply them, whatever the heck that even means, my gut tells me that the answer should be a vector. Again, there's no particular reason for that. It's just, to me, I think it feels right. And to you, you might agree or disagree. You might think that something tells you that it should be a scalar. The actual answer to this question is that it depends. It depends. And there's actually two ways to go about it. Okay? There are two ways to multiply this. We're going to talk about specifically the dot product in this way. And the other one is called the cross product, which we'll address later. Okay? To address what this means, I actually want to go back and reference the scalar, not scalar plus scalar. I want to actually talk about scalar times scalar. So let me pull up another illustration here. Alrighty, welcome back. So what I've drawn here is I've drawn two number lines and on the first number line on top, I'm going to illustrate how we could, I'm going to show how we can illustrate multiplying scalars. And it's going to look kind of weird, but I saw this explanation, and to me, it makes the most sense when it comes to rationalizing the dot product, and like it makes sense of why the dot product is the way it is and why it looks so weird. Alrighty, so multiplying scalars. So if I want to do 3 times 5, so we can represent the number 3 with a little arrow here. Okay, so I'm going to go out to roughly 3. Ignore the scale here. So this is going to be 3, and it points off about that way. Oopsies, sorry about that. So that's 3 right there. The vector 5 reaches a little bit farther and goes right there. So I'll draw that one like so. The number 5. Excuse me. So when we say 3 times 15, what are we actually saying to do? Well, it means to take one of the vectors, and again, it doesn't really matter which one because we know we know that multiplication is commutative. It says to essentially apply one vector a number of times equal to the other one. So what do I mean by that? It simply means take this vector, say the 3, or one quantity, the 3, and apply it 5 times. So that would mean, well, there's 1, 3, there's 2, 3, 4, and then 5. I didn't have enough room. And the end result, it goes from 0 to wherever that ends up, which for this example would be 15. Kind of a weird way to think about it. You don't typically think about it when you're just multiplying 2 numbers, but this is a way to illustrate it. Now, when the numbers, when you have a negative and a positive, it, again, essentially works the same way. It's just we kind of have learned at this point. If that's the case, then you turn it negative. But we can also illustrate it like so, because pretend that the negative 3 is represented over here. Oops, excuse me, pointing to the left. And again, the 5 goes over here. And so this just says, okay, use the negative 3 vector 5 times. Oh, okay, so that says that's 1. So I'll just run that once, twice, 3 times, 4 times, 5 times, and that's how we end up with negative 15. Okay? So let's try to use that same explanation to talk about how to multiply vectors. Okie dokie, so I'm back, and so we want to essentially multiply these 2 vectors. So the way we're doing it in this video is the dot product. Again, there's another way to multiply called the cross product, which we will address later. So this is, again, one interpretation, one way to multiply vectors. The dot product we will denote and write it like so. Let's keep the color coding here. We have A dot B. It's literally called A dot B. You can't just say A times B because the person's going to ask, what kind of multiplication are you doing? So again, we're going to do A dot B with a big dot right there. And we're going to try to figure out what that is. Okay, so if we look at the scalar example, how we multiply scalars, one requirement that we needed, well, we didn't really talk too much about the requirement exactly, but one thing we noticed is that the 2 vectors, that, quote unquote, that we represent, or the 2 numbers that we represent with these little arrows, are pointing along, or they're collinear. So they lie along this single number line here. Doesn't quite work out the case when we have vectors in multiple dimensions. Quite clearly, they could be pointing off in really any direction. So the question is, really, how do I represent, the 2 vectors pointing off in some direction and applying their kind of values to each other? Because that's what's happening over here in scalar multiplication. This 3 is pointing off to the right. The 5 is pointing off in the right. And so you apply the 3 kind of 5 times. In this case, the negative 3 is pointing off to the negative 3 is pointing off in the left direction. The 5 says, okay, apply it 5 times, positive 5 times specifically, which means keep the same direction. And so for us, we want to keep these vectors kind of in line, but they're obviously not. So what we do is we ask ourselves, well, how much of A, and again, by the way, this could be done the other way as well, how much of A is pointing in B's direction. Here's another way to say that. If we kind of break A up into two pieces, components, we can think of it like this. A has a little bit of its vector pointing along B, and it also has a component vector that is perpendicular to B, like so. If you remember from the last video, we actually know exactly what this vector is. This vector right here, I called it the quote-unquote shadow vector, but really, this is the vector projection of A onto B. And if you remember the formula from last video, that formula is, I'll write it down here, the projection of B onto A, again this is a vector, is the magnitude of A times the cosine of, times the cosine of the angle between them, whatever that angle happens to be, divided by B. Actually, I'm going to write it like so. I'm going to write it a little bit differently. Times 1 over the magnitude of B times the vector B itself, right? Again, remember, let's take a second here. This represents the unit vector in length, the unit vector pointing in B's direction, and this is the length of the shadow, or length of the projection. Okay. And so we're actually really, really close to what we have, to what we're looking for. Again, we're really just looking for, once we get these vectors in line, or along the same line, again, like on the same number line here, and then just multiplying their quantities. And so what we're really looking for with A dot B, let me drag this up a little bit, excuse me. A dot B really is the product of B, sorry, the magnitude of B, right? It's just like the magnitude of this vector right here was little 3. The product of the magnitude of B and the magnitude of, and the vector A in B's direction. This right here is the vector projection. It's right here. We actually don't care specifically about the vector, but we care how long that shadow vector, that projection vector is. And so the dot product, if we simplify this, well, we know what the magnitude of B is, or we could calculate it easily. Turns out that A dot B is simply equal to the magnitude of B times the length of the projection of A onto B, meaning magnitude of A cosine theta. And so this is the dot product. Really, all it's doing is taking, okay, once you get the two vectors in line, and again, they're not exactly the same thing. Like this projection, the vector projection is not A. It's simply representing, how much the vector A points in B's direction. You could also calculate, the vice versa. You could also calculate, B dot A and get the magnitude of A times the portion of B pointing in A's direction. Okay, this is not really easy to explain, and I think that's why I haven't found that many videos on it. And this is simply my attempt at explaining it, and I totally acknowledge that this might not make the most sense to you, but I do appreciate if you've made it this far, that you're trying. Okay, so essentially A dot B, again, I'll just repeat it because repetition helps me. A dot B, again, this is one way to multiply vectors, is the product of one vector, or the length of one vector, the magnitude of one vector, and the magnitude of the other that is going in the same direction as it. Notice, by the way, in this case, they're going to be positive. This enters a number. This is a scalar. So when you do the dot product, you always end up with a scalar, a number, right? This right here is a scalar. When the two vectors are pointing in the same direction, and what I mean by that is this angle is acute, it will be a positive because these two vectors right here, they're pointing, again, in the same direction, and these two vectors are both vaguely pointing in the same direction. If you had an example like so, I'm running out of room here, like this, then the dot product is going to be negative because this projection would be projected, well, downward this way. And so they'd be pointing in opposite directions, excuse me. Okay. Whew. Okay, so this is the dot product. Now, there is actually an even faster way to calculate it, but before we even get there, we need to agree that this actually is the dot product. Okay, so I hope that made sense. It probably did not make too much sense, but that was my attempt at it, and I hope that helped at least some of you. Again, I appreciate if you watched through this whole thing, and let me know if you have questions. Alrighty?